Previously on QuantSlob. And now. That was some pretty exciting stuff there, huh? Greetings and welcome to another installment of QuantSlob. This is 41 in our basic application series, and this time around we're going to continue on with part 2 of our exhilarating simple linear regression series, calculating the regression line from population data. Now, keep in mind that we're performing descriptive statistics. That is, we're viewing our data set as our population. Fortunately, calculating our SLR, simple linear regression line slope, and y-intercept from data is both fairly simple and straightforward. There's a couple common ways to do this. We can, for one, calculate our slope as a function of covariance between x and y, or we can calculate our slope as a function of correlation between x and y. And we're going to go ahead and use the covariance method. It's maybe just a little bit more direct. In the context of regression, we typically refer to our predictor or independent variable as x and our outcome or dependent variable as y. Generically anyway, it's just a notation thing. We say we regress y on x. Okay, our regression line function. Take a look. Notice our notation. We call our population y-intercept beta sub 0, lowercase beta, beta, the second letter in the Greek alphabet, and our population slope beta sub 1. Our population slope can be calculated from data by dividing the covariance between x and y by the variance of x. And once we've calculated our slope, we can calculate our population y-intercept by subtracting the product of our population slope with the population mean of x from the population mean of y. So this is all very tactical here. So the ingredients we need to calculate a regression line are the population means of x and y, the population covariance between x and y, and the population variance of x. So for the population mean of y, we sum up all the y values in our data set and divide by the number of observations. Same deal for x. For the covariance for each observation, we center both x and y, mean center, subtract out the means, respectively, x and y. We take the product of the two, and then after that we sum up all these products and divide by the number of observations. Lastly here, for the population variance of x, for each observation, we center x, center it, mean center it, and square it. Same thing as multiplying it by itself. Then after, we sum up all these squares and divide by the number of observations, capital N, number of observations in our population. So let's look at a very simple little make-believe example, just 4 elements, 4 observational units. Notice here that we've actually included measurement units here to add a little excitement. X is in units kilograms, Y is in units meters. For our immediate purposes here in these calculations, these units will be dealt with mostly transparently. So let's take a look at a scatter plot of our data here. Little visual, nothing wrong with that. Looks like the x and y values from our little make-believe data set form the apices of a square. Nothing particularly exotic here. So let's calculate the population mean of y. Sum up all the values, we get 0. 0 divided by 4 is 0. This is in units meters. Let's calculate the population mean of x here. Take the sum, 0, 0 divided by 4, 0. Pretty simple. X is in units kilograms. We'll set those two calculations in the bank, set them aside, so to say. Okay, now let's calculate our covariance and variance. Notice we're using a capital delta, the fourth letter in the Greek alphabet, to denote the mean difference. And we're doing this simply to conserve space in our table, conserve horizontal space, so we can fit it on the slide. The population means for both x and y are 0, so the centered values will simply equal the original attribute values. Okay, for the covariance, -1 times -1 equals 1. -1 times 1 is -1, and so on. And the grand sum of all these products, very simple enough, is 0. For the population variance of x, -1 times -1 is 1. 1 times 1 is 1. We sum up all these squares and we get 4. So 0 divided by 4, the population size is 0. 4 divided by 4 is 1. Easy enough. Our x-y covariance is 0. Our x variance is 1. So we just keep turning the crank and solve for our population parameter slope and our population parameter, the y-intercept. Okay, admittedly, not a very spectacular line equation, but it's a line equation nonetheless. This is our population regression line equation given our population of the 4 observations. So let's plot this line on our scatter plot here. Our regression line is simply just y equals 0 everywhere. Happens to be our Cartesian x-axis. Needless to say, our line calculation preserves measurement units. Our predictor response covariance has units x times y. Our predictor variance has units x squared. The result is that our line slope is in units y over units x. In our previous example, our slope would have units meters over kilograms, or meters per kilogram. The consequence is that when we multiply a value of x by the slope, the units x cancel out and we end up with units y. So here in our example, if our slope is in units meters over kilograms, when we multiply it by a value in units kilograms, the kilogram units, measurement units, cancel out and we are left with a value in units meters, which is our units in y. This is precisely what we require here. Also notice we can calculate our slope directly as a function of our sum of products in the numerator and our sum of squares in the denominator. You can see here that the 1 over n and the population size cancel out in the fraction. Just simplifies things a little bit, and that's it. That's going to do it this time around. Thank you very much for tuning in. Don't forget to stay tuned for more QuantSlob.